This is the second half of the lesson. The first part of the lesson, we discussed about different types of magnetic field, the different patterns of magnetic field generated due to the flow of current in different shape of conductors. The first one we have seen, when current passes through a straight conductor, it produces concentric circles of magnetic field lines. Then we have seen a single loop of wire forming a special pattern of magnetic field lines, and also after that a solenoid, strong magnetic field inside the solenoid. We can use that magnetic field for converting a soft iron into a magnet. It is called electromagnet. So in all that previous discussion, what we have seen, whenever current flows through a conductor, whether it is a straight conductor or a single loop of wire, or if it is a solenoid, a cylindrical loop of wire, or if it is any shape, doesn't matter. Whenever a current flows through a conductor, it will produce a magnetic field. The shape of the field pattern, magnetic field lines, depends upon the shape of the conductor. That was the discussion in the previous part, and also in the last part of that we have seen when a current flows through a conductor placed in a magnetic field, it experiences a force, and the direction of force is given by Fleming's left-hand rule. Okay, now we are going to the second part of the lesson, that is electromagnetic induction. Who is the father of electricity? Michael Faraday. He was considered as father of electricity because of one simple discovery, that is electromagnetic induction, that we are going to explain today. He was in the year 1830, nearly 200 years back. This discovery was how many years back?
200.
This great person, he discovered the phenomena called electromagnetic induction. Till that day of discovery of electromagnetic induction by Faraday, the entire world was in perfect darkness, because on those days electricity was discovered, but that electricity produced was only from a battery, from a cell. In a cell we can convert chemical energy into electrical energy. But the electricity right now we are using in our building, in our home, it is not electricity generated from a battery. It is the electricity generated from an electric generator. And in an electric generator, the principle of working of all electric generators, we have three types of main generators. One is hydroelectric generator, the other one is thermal, and third one is nuclear. In all these three generators, electricity is produced by the principle of electromagnetic induction discovered by Faraday. Except solar cell, all other generators, whether it is hydroelectric, thermal, nuclear, in all these three generators, electricity is produced by the principle discovered by Faraday, that is electromagnetic induction. That is why Faraday was considered as father of electricity. Got it?
Yes, sir.
Now, there is a story behind this discovery. Faraday was born in a poor family. Even he did not get the formal schooling like us. He did not go to school. And because of the very poor situation of his family, he used to help a person in a bookbinding shop. In early childhood itself, he used to work with a person in a bookbinding shop to earn some money for the bread of his family. And one good habit of Faraday was, whenever he get a book for binding, after binding, he returned the book only after reading the book completely. So whenever he get a book for binding, he used to read that completely. With that habit, he learned lot of things, and he was able to read lot of books without going to school or library, from the book binding shop. So the story was like this. One day, Michael Faraday, he got a small book written by Andre Marie Ampere. You know Ampere. What is Ampere?
Unit of current.
It is the name of a scientist, and the name of the scientist Ampere is taken as unit of current. Faraday was reading a small book written by Ampere. In that book, Ampere explained the different way of producing magnetic field, like passing current through a straight conductor, a coil, and how to make electromagnet. The magnetic effects of electric current was explained in a small book written by Ampere. And Faraday got that book for binding, and Faraday was reading that book. And when he was reading the book, what is the difference between watching a video and reading a book? Suppose you are watching a movie, and the same movie, it is there in the form of a novel, and you are reading the novel also. What is the difference between watching a movie and reading a novel? Imagination
Yes, sir.
can be different, but if you are watching a video, it is limited. What is there on the screen, that only will be coming to our mind. But when we are reading something, our mind will expand. We will get more chance to imagine. Our imagination has no limit. So usually, if you read a book, your mind will expand. So it is better to create a habit of reading rather than watching too much videos. And what happened that day, when Faraday was reading the book written by Ampere, a new idea came to the mind of Faraday. A new idea came to the mind of Faraday. You know this idea? What I have written on the screen. I is inverted.
Idea can change the
That only. See, this is the tagline of Idea mobile service provider in India. An idea can change your life, isn't it? But this idea came to the mind of Faraday. It changed the entire world, not only the life of one person. This idea changed the entire world. And what was the idea came to the mind of Faraday while he was reading the book written by Ampere? This was the idea. He thought like this. Faraday thought like this. Everything in this universe is paired. Everything has two effects. If there is positive charge, there is negative charge. If there is light, there is darkness. Okay? If there is day, there is night. If there is male, there is female. If there is right hand, there is left hand. If there is up, there is down. This idea came to the mind of Faraday, and he thought like this. In the book written by Ampere, it was explaining when a current passing through a straight conductor, it produces a magnetic field in the surrounding. When a current passes through a coil, it produces magnetic field. When a current passes through a solenoid, it produces magnetic field. And even we can make electromagnet. Then Faraday thought in the reverse way. Everything has two effects. If a current passing through a conductor can produce a magnetic field, why can't a magnet produce electric current? Good idea, isn't it? Why can't a magnetic field produce electric current? Now electric current is producing magnetic field. We have seen that. We have seen many experiments. In all that experiment, what we have seen, when current passes through a wire, it is producing magnetic field. The first experiment of Easton. What Easton discovered, when current was passing through a wire, a magnetic needle deflected. Because when current passes through a wire, it produces a magnetic field. The concentric circles. So Faraday thought in the reverse way. If a current can produce magnetic field, why can't magnetic field produce current? With that idea, he started doing experiment. And Faraday was having a simple arrangement. You can see in this figure. Can you see the figure?
Sir.
He was having a simple
sir.
copper wire. He was having a coil of copper wire, insulated copper wire, and that was fitted with a small galvanometer. This is galvanometer. A galvanometer is a simple device. Inside there will be a magnetic needle and some coil. And this galvanometer is used for detecting very minute current. If there is very small current in the circuit, galvanometer needle will show some deflection. And that galvanometer was designed by Ampere, and that also was explained in the book. So Faraday made a small galvanometer and a coil and a bar magnet. He was having this much things: a bar magnet, a copper coil, and a galvanometer for detecting the presence of current. And he did many experiments. He tried different ways. He could not see any deflection in the galvanometer. If a current is produced in the coil, galvanometer, it must show some deflection. The needle will deflect. But he could not see any deflection in the galvanometer after doing many trials, many experiments. And one day in an angry mood, Faraday was throwing this magnet. Faraday was throwing this magnet into the coil. So when the magnet was thrown into the coil, that was the first time in the history electricity was produced by this method. What he could see, when the magnet was thrown into the coil, the galvanometer deflected to one direction. When the magnet was stationary inside, it came back to zero. The needle came back to zero. Again, when he was withdrawing, when he was taking the magnet out of the coil, the needle deflected in the opposite direction, reverse direction. If you keep the magnet inside the coil stationary, no deflection, no current is produced. But if you keep on moving the magnet inside, you can see the needle deflecting on either direction, depending on the direction of motion of the magnet. And this principle is the working principle of all types of electric generators, hydroelectric, thermal, nuclear. That's why Faraday was considered as father of electricity. Now here what happens, why there is a deflection in the galvanometer when the magnet is moved? What can be the reason for this?
Yes, sir.
Do you remember magnetic field lines?
Yes.
What is magnetic field lines? They are
Sir,
imaginary
lines.
curves. They originate from north pole and terminate to
South pole.
outside the magnet. If you take a bar magnet, you remember the field lines of a bar magnets are like this. They originate from
Yes.
north pole and terminate to south pole, this direction. Suppose this magnet is taken into this coil. If the magnet is taken into the coil, then what happens? Now you can see these magnetic field lines surrounding the bar magnet. They are linked with, they are associated with the coil, the turns of the coil. When you move the magnet inside, what happens? The magnetic field strength associated with each turn will keep on changing, because you know at north and south pole there is strong magnetic field, at the middle it is weak magnetic field. So when you move the magnet inside the coil, there will be a change in magnetic field associated with each turn of the coil. Now listen all of you, this is the statement of electromagnetic induction. According to Faraday's law of electromagnetic induction, whenever there is a change in magnetic field associated with a conductor, it will induce a current. This principle is called electromagnetic induction. Whenever there is a change in magnetic field associated with a conductor, it will induce a current. Whenever there is a change in magnetic field associated with a conductor, it will induce a current. This is called electromagnetic induction. Suppose in your home, at one corner of your room, you keep a large turns of copper wire, and keep inside that a strong magnet also. Can you take continuous current from this? Will you get current from that?
No, sir.
If it is possible, it's a good idea, isn't it? No need to pay an electricity bill. Keep a large turn of wire at the corner and put a magnet inside and get enough electricity. It's not possible. What we have to do?
We need to change,
We need to move the magnet. We need a change in magnetic field. Keep this point in your mind. A constant magnetic field can never induce a current. A constant magnetic field can never produce a current. We need a change in magnetic field, and for bringing a change in magnetic field, we need to move a magnet. And for moving the magnet, you have to use some mechanical energy. Okay? You can use the speed of flow of water from a dam reservoir to rotate a magnet. You can use the pressure of steam produced in a boiler by burning diesel or kerosene in a thermal power station. You can use the high pressure steam produced in a nuclear power generator, and that steam pressure can be used for rotating a turbine. The turbine can be connected to a magnet. When the magnet rotates between a coil, it can induce. Got the point?
Yes, sir.
So, for inducing electric current, we need a change in magnetic field. For producing a change in magnetic field, we need to move the magnet. And for moving the magnet, we can use different forms of mechanical energy. A generator is a device which converts mechanical energy into electrical energy by using Faraday's law of electromagnetic induction. A generator is a device which converts mechanical energy into electrical energy by using the principle of electromagnetic induction. Some questions. All are ready? Already I told you a current can be induced only if there is a change in magnetic field. The first question, if I want to increase the current, I want to increase the current I produced in the coil. Okay. For increasing the current produced in the coil, what are the possible ways? What are the possible methods by which I can increase the induced current?
Move the magnet.
Okay, correct. Strength of magnet, increase the strength of magnet, isn't it? If you use more stronger magnet and a weak magnet, you will get same current?
No, sir, we should use strong magnet.
Yeah, so the strength of the magnet. You can increase the current by increasing the strength of the magnet. That is the first point. Strength of the magnet. Then anyone else, another method? To increase the current I, okay, induced in the coil. How can we increase the strength of current? One method is by increasing the strength of the magnet. Then,
Sir, if we increase the speed when the magnet moves.
yeah, very good. That's a good idea. By increasing the speed of motion of the conductor. Speed of motion of the conductor.
Sir, if we increase the number of coils.
Very good. That is good. That is the third method. By increasing the number of turns of the coil. These are the three different ways by which we can increase the current induced in the coil. By increasing the strength of magnet, if you use a stronger magnet, there will be more magnetic field lines. Then if you move the magnet, there will be sudden change in magnetic field. And if there is a large change in magnetic field, large current will be induced. The second one, if you move the magnet very fast, then also change will be very fast. If change is very fast, more current will be induced. Do you have a bicycle in India with a headlight?
Yes, sir.
When you are riding the bicycle, when you pedal it slowly, you can see headlight will give very little light on, isn't it? When you pedal the bicycle very fast, you can see the headlight become more brighter. What is the reason? Okay, at the back side, at the back tire, near to the back tire, there is a dynamo, there is a small generator, inside there is a magnet and a coil. And when you are pedaling, the rotor of the generator is touching the tire. And when the tire rotates, the rotor also rotates. Rotor is inside, it is connected with the magnet. When magnet rotates in the coil, it induces current. When you pedal the bicycle slowly, magnet rotates slowly, so less current is induced, so the headlight will be having very dim light. Isn't it? The headlight will give very dim light. When you pedal it very fast, the magnet rotates very fast, you get high variation of magnetic field, more current will be induced, so the headlight become more brighter. Then if you have more number of turns, if you make many turns of the coil, more current will be induced. So if you take any generator, the main parts of a generator is a coil and magnet. A generator means this much only, a coil and magnet. You need to move either the coil or the magnet. One should be stationary. You can keep the coil stationary, move the magnet. You can keep magnet stationary, move the coil. In both the case, current will be induced.
So if both are moved.
If both are moving, there will be no change in magnetic field. I will show you that experiment. Any one should be moved. There should be a relative motion between the magnet and the coil. 1 second, I want to switch off the light in front of me. Now, all of you see this one? Okay, this is same like the experimental arrangement was with Faraday. So instead of Faraday, in Faraday's experimental arrangement, the coil is same like this. Okay, this is the copper coil, insulated copper wire, and the two ends of the copper wire is connected to a galvanometer in Faraday's experiment given in the figure. But here, instead of galvanometer, two LEDs are connected. And these two LEDs, you know, LED has positive and negative. It is not like normal bulb. If you give battery positive to positive of the LED and negative to negative of the LED, then only it can glow. If you give reverse connection to the LED, it won't work. It will not glow. It will not give light. Got it? So here these two LEDs, positive of one LED and negative of other LEDs are interconnected, and vice versa. And that two common points are connected to two ends of this wire. Means these two LEDs are connected at the two ends of this wire, at the two ends of this coil, in reverse way. One LED positive, other LED negative. Then again one LED positive, other LED negative to the other end. So when current flows through this, depends upon the positive and negative of the current direction, only one LED can glow. other will not glow. Okay, so at the back side it is interconnected here. Okay, there is connections here. The two LEDs, okay, plus and minus are connected together. Another LED, plus and minus of two LEDs are connected, and the two common points are connected to the coil. Now I have a magnet also. This is a strong magnet. Okay, when I move the magnet inside the coil, you can see current will be induced. And suppose now I am moving north pole. North pole I am withdrawing, taking out of this coil. That time, out of these two LEDs, only one will be glowing, because positive and negative of two LEDs are interconnected. They are cross connected. Depending upon the direction of current, only one LED can glow, other will not glow. You see here, it's glowing.
Yes, sir.
Which one is glowing now?
The right
Left,
side.
the one is at the left side, in my left hand. This is my left hand.
Oh, yes,
Okay, so one LED at my left side is glowing now. Now I am changing the pole. Okay, I am reversing the magnet. Now you see which one is glowing. Now the right one is glowing, correct?
Yes.
Because direction of
sir.
current changed. Because when I change the direction of magnetic field, the direction of current also changed. Now left is glowing. When I reverse the magnetic field, you can see the right one is glowing. Okay? This is a generator. It is producing electricity and the LED is glowing. And what is there in the generator? A magnet and a coil. A magnet and a coil. That's enough. In practical generator, in the commercial generator, we will have more number of turns, and very strong electromagnet will be used, and very large number of turns will be used, and the speed of rotation will be very fast. In India, electricity is producing 50 hertz cycle, 50 hertz frequency. Means every second in the power generator, in the powerhouse by using the speed of water flow from the dam reservoir, the magnet is rotated 50 times in 1 second. 50 times in 1 second. So it produces very huge amount of electricity, and that is coming to our home, and that we are making use at home. Got it? Now in this case, in this experiment, if I move this magnet slowly, is the LED glowing? Is it glowing?
No, sir. No, sir.
Why not? It is producing change in magnetic field, but the current produced is not enough for glowing the LED. But if I increase the speed, now it is glowing. When I increase the speed, more change in magnetic field will induce more current, and that current is enough for lighting the LED. So
Yes.
this is electromagnetic induction. And in Faraday's experiment, only the difference was, instead of this LED, one galvanometer was connected here. And when galvanometer was connected here, when we move the magnet from north is moved, galvanometer will show deflection in one direction. If south is moved, it will show opposite direction. Now here, one left LED is glowing at one time. When I change the direction of magnetic field, then right LED is glowing. Same like that, galvanometer will move towards right and left if you change the direction of magnetic field, or if you change the direction of motion of the conductor. Galvanometer is a device used for detecting the presence of current. Means when we move the magnet inside, whether current is produced or not, that we can detect by using galvanometer. That is given in the figure, isn't it? The importance of galvanometer is that very minute current, very minute current itself we can detect. But LED, with LED you cannot detect very minute current. We need a large amount of current for glowing this LED. So when I am moving this magnet, current produced is very large, not very small. That's why it is glowing. But in Faraday's experiment, it was a very small magnet, not this much powerful magnet. It's a very powerful magnet. During the time of Faraday, LED was not discovered. So there was only galvanometer, which can be used for detecting the presence of minute current. But right now, instead of galvanometer, we use the LED. LED shows the presence of current by glowing. If the LED is glowing, means current is produced. If it is galvanometer connected, if galvanometer needle deflects, it shows current is produced. Now one more thing, when a current is produced in the coil, when we move the magnet, a current is induced in the coil. And the strength of the current, as you told, we can increase the strength of the current by increasing the strength of the magnet or magnetic field, by increasing the speed of motion of the conductor or the magnet, and also by increasing the number of turns. Now one more question is there, in what direction the current will be induced? Whether the current will flow in clockwise direction from this side or anti-clockwise direction, or the current in the external circuit, the current will flow this way or this opposite direction. In which direction current will flow through the external circuit? That direction of induced current is given by Fleming's right hand rule. Before we study Fleming's left hand rule, isn't it?
Yes, sir.
What was Fleming's left hand rule? Stretch the thumb, index finger and middle finger of the left hand mutually perpendicular to each other.
Yes.
And then if the index finger points in the direction of magnetic field, middle finger in the direction of current, then thumb will give the direction of force acting or the motion of the conductor.
Force.
The same thing if you apply right hand, that will give the direction of current. Okay, in the right hand rule, Fleming's right hand rule, same FBI, force, FB magnetic field, I current, FBI. So easy to remember FBI. In FBI, in a generator, we are giving a force, we are moving a conductor. Thumb points in the direction of motion of the conductor, and we are providing a magnetic field. Then this middle finger will point in the direction of induced current. Got it? So the right hand rule is for generator, left hand rule is for electric motor. Both are FBI. In electric motor, we are giving a magnetic field, we are giving a current, and we are getting a force. And by that force, it rotates. The motor rotates. In generator, we are giving the force, we are giving a magnetic field, and we are getting an induced current, middle finger, FBI. Got it? Okay? So the direction of induced current, in a conductor when it is moving a magnetic field is given by this right hand rule. All of you can see the picture on the screen?
Yes, sir.
Okay. Here, if you stretch the three fingers of your right hand, that is your thumb, your index finger and the middle finger, mutually perpendicular. This angle is 90 degree. Okay, this angle is 90 degree, this two also 90 degree. All are at 90 degree each other, mutually perpendicular to each other. Then if your thumb points in the direction of motion of the conductor, okay, here thumb is in the direction of motion of conductor, not magnet, direction of motion of conductor or force acting on the conductor. The index finger points in the direction of magnetic field. Then the middle finger will give the direction of induced current. The middle finger will give the direction of induced current. In the figure you can see here, when you stretch your thumb, the index finger and middle finger of your right hand mutually perpendicular to each other. And if this thumb represents or the thumb shows the direction of motion of the conductor or force acting on the conductor, and the index finger points in the direction of magnetic field, applied magnetic field, north to south, then the middle finger will give you the direction of induced current. All same direction, same like left hand rule. But here, current we are giving magnetic field and force, and we are getting current. In left hand rule, current and magnetic field we are giving and force we are getting. Okay?
Yes, sir.
Now listen all of you. What is electromagnetic induction? Whenever there is a change in magnetic field, it will induce a current. And for producing the change in magnetic field, we can move a magnet inside a coil. Okay? And there is another method, a different method, by using that also we can produce current. Now see here, the next experiment, suppose here there is a cell connected, a DC cell is connected, and there is a switch here. Suppose here there is a switch, the cell is connected. This is also electromagnetic induction, but here without magnet we can induce current, without magnet. So what is happening here? There are two coils, coil 1 and coil 2. Coil 1 you can call primary coil, coil 2 you can call it secondary coil. The primary coil, coil 1 is connected to a cell and a switch, okay. Coil 2 is connected to a galvanometer, only galvanometer, no source of electricity, nothing is there, only galvanometer. Galvanometer is a device only for detecting presence of current. So what we can observe here, when we switch on this circuit, when I switch on here, we can see some deflection in this galvanometer. What can be the reason? There is no magnet here, no magnet, no bar magnet, only cell is connected. Okay, when I switch on, we can see a deflection here. When you keep it switch on condition, there will be no deflection. Needle will go back to 0. And at the time of switching off, when you switch off here, that time again there will be deflection in the opposite direction. So we can see deflection in the galvanometer at the time of switch on, switch off in two reverse in opposite direction. If you keep it continuously switch on, there will be no deflection.
When the current passes through those wires, I think those wires might turn into temporary magnets.
So when a current, as we have studied from the previous session, when a current passes through the solenoid, this coil, one end becomes north pole, other becomes south pole. And there are magnetic field lines passing like this, isn't it? So these are the magnetic field lines created when current passes through this one. When current passes through the coil number 1. And since the coil 2 is also placed very close to coil 1, the magnetic field lines of coil 1 is linked with the secondary coil also, coil 2 also. So whenever there is a change in magnetic field, it will induce a current in the secondary. This is the working principle of transformer. Only at the time of switch on, switch off, there will be change in magnetic field. If you keep on switch on condition, there will be no deflection here. It will come back to 0. Why the deflection come back to 0? When you keep it switch on condition, a current can be induced only by a change in magnetic field, a varying magnetic field. A constant magnetic field can never induce a current. If you keep it switch on condition, there will be magnetic field, but it will be a constant magnetic field. And that constant magnetic field can never induce current in the secondary coil. But when you switch on, switch off the circuit, there will be an increase or decrease in magnetic field. That time there is change in magnetic field, so current will be induced in the secondary coil. Current can be induced only if there is change in magnetic field. And change in magnetic field we can produce by switching on and switching off the primary. So if you keep on, switch off, you can see here deflection on either side. Now listen all of you, instead of battery or instead of cell, suppose in the primary it is connected with an alternating current, AC supply. This is the symbol of alternating current. We have two types of current, AC and DC, alternating current and direct current. Right now the electricity we are using in our building, is it AC or DC?
AC.
The commercial electricity we are using at our home, it is not DC, it is AC. This is the electricity, okay? It is not DC, it is AC. Now AC means the AC will be flowing in two directions, positive and negative. Every second direction will keep on changing. India, the AC produced in India is having frequency 50 Hertz. 50 Hertz means in 1 second the AC we are using right now in our building, here in Saudi Arabia it is 60 Hertz. In Saudi Arabia AC is produced in generator, alternating current is produced in generator with the 60 Hertz frequency. 60 Hertz frequency means 1 second 60 times the magnet will be rotating. In 1 second 60 times the magnet will be rotating. When the magnet rotates 60 times in 1 second, 120 times direction will change. In one moment, if the current is flowing towards right, the next moment current will be flowing towards left. So in one moment, if here is north pole and this side is south pole, the next moment this side becomes south pole and this side becomes north pole. And if it is 60 Hertz AC is flowing, 120 times north and south will change. 120 times north and south will change. 3 times a magnet is rotated inside, same effect will be produced if an AC is passed. Got the point? So if an alternating current, not the current from a battery, the supply current right now in our building is AC, alternating current. In India it is produced 50 Hertz frequency, means the magnet will be rotating 50 times in 1 second. So 1/2 rotation, current will be flowing towards right, second half will be left. So in 1 second 100 times direction will change. So 100 times magnetic field direction will change. It means there will be continuous change in magnetic field. So if it is AC, there will be a continuous current in secondary. If AC is flowing through the primary, there will be continuous current induced in the secondary. So we can induce current in a coil not only by moving a magnet, but also we can induce current by changing the current in the primary. We have two coils, primary and secondary. If you change the current in the primary, it will induce current in the secondary. Because current in the primary changes, it will produce magnetic field, variation in magnetic field, and that magnetic field is linked with the secondary also, and it will induce a current in the secondary also. It is called mutual induction. Mutual induction, it is the same principle of Faraday, and it is used in the working of transformer. One question. So here I explained two different methods of inducing current. One is by moving magnet, that was discovered by Faraday, moving magnet inside a coil. Now the second one, by using two coils without magnet. Two coils without magnet. The first coil is connected with a varying current, change in current. Secondary coil 2 is connected only with a galvanometer, and it induced a current in the secondary because of the change in current in the primary. My next question is,
Yes, sir.
suppose you are here, okay, and I am giving you in your hand a large number of turns of coil. You have a large number of turns of coil in your hand, copper, okay,
Yes.
and suppose you are running fast, you are running very fast through the ground, and this coil is connected with a galvanometer. There is a galvanometer connected to the coil,
Yes.
and when you are running fast, will this galvanometer show any deflection? Okay, in your hand I am giving a large number of turns, copper wire, and that copper wire is connected with a galvanometer also, and you are running very fast, okay, through the school ground. Suppose you are in school ground, we are doing an experiment, you are running very fast. Is there any chance for inducing current in this? There is.
I think
There is, because earth is a magnet. There are magnetic fields all around, okay.
yes.
So when you are running fast, you are producing a change in magnetic field associated with the coil. So when you run very fast, the magnetic field is keep on changing. So there is a chance for inducing current in the coil. So the galvanometer may show some deflection because earth is a magnet. It happens normally in vehicles. When we are in a flight, the flight is a conductor. There are magnetic field surrounding the earth. So when the flight is moving in the magnetic field of earth, it is inducing current in the body of the flight. It is inducing current in the metallic body of the flight.
Yes, sir.
And you might have observed some people they vomit if they travel long distance in bus and also in flight.
Yes.
But no one will vomit if they travel in a train. If a person has the vomiting tendency when they travel long distance on road or in flight, such person will never vomit if they are traveling in a train for 2 or 3 days. You know the reason? The vomiting tendency is there in some people because when we are sitting in a bus is a conductor and its tires are made up of rubber, and flight is also a conductor. It is not touching the earth in space. When they move very fast, they induce current. In the metallic body of the flight and the bus, it induces current. And that current will come to our body also because we are touching the metallic part of the bus or the flight. And when that slight small amount of current reaches to the body, some people will have vomiting tendency. But they will never vomit if they are traveling in a train because of this motion sickness. You know what is the reason? Anyone, can you tell the reason? You compare bus, flight and train.
Train's tire or metallic.
That is the reason. In the train also current will be induced, but the tires of the trains are metallic, steel, and whenever current is induced in the body of the train, that will be conducted to the earth. It is continuously earthed. So the current will flow to the earth, it won't flow to the body of the person. Always moving on the rail, and the train, the tire and rail are in contact, both are metallic, so the current induced will flow to the earth. So the person will not feel vomiting tendency. Now listen all of you, for this second method, inducing current in the secondary by changing current in the primary, we have an experiment. That experiment is in my own YouTube channel. I will show you. So whenever there is a change in magnetic field associated with a conductor, it will induce a current in it. That is the basic principle of electromagnetic induction. It can be again demonstrated by another experiment. Here, this is an electric bouquet. It consists of two coils. This is the primary coil and this is the secondary coil. The secondary coil is fitted with some LEDs. Okay, only it's a copper coil. It is insulated all around, and it is the two ends of the wires are connected to an LED panel. And the primary coil, this primary coil I am going to connect directly to the electric supply. So when I connect this primary to the electric supply, and it is kept in a core, in a software core, like this. Now, the primary this is software core. Primary is kept on a stand which is fitted with a software core. Now, when I move this secondary coil near to the primary, since an alternating current is flowing through the primary, it is producing a flux change, and due to the flux change, it is inducing current in the secondary, the LED is glowing. When I move this away, when the magnetic strength decreases, the light intensity also reducing because induced current reduces. Now it is not glowing at all because no induced current is produced. When I move it slowly downward, you can see the brightness of the LED increasing and become maximum when it is very close to the primary coil. So whenever a current flows through the primary here, it is producing a changing magnetic field, and because of that changing magnetic field, it induces a current in the secondary coil.
Yes, sir.
How the LED panel is glowing because of the current induced in the secondary. There is no connection between them. Have you seen there is a mobile charger? No need to connect the mobile to the circuit. Have you seen that one? There will be a pad only. There will be a pad for that, charging pad. The pad you have to connect to the supply. There will be a charging pad like this, and this pad you have to connect to the supply on the plug. And mobile you have to just keep on the surface. Just you keep your mobile on the surface. Wireless recharging. You have to keep just the mobile on the surface of the pad. No need to connect. No need of wire connection. Pad will be connected to the charging pad will be connected to the supply. What is this process actually? Electromagnetic induction. Inside the pad, if you open inside the pad, there is a primary coil, and it is connected to AC, alternating current. At the back side of your mobile phone, there is a secondary coil. When you keep the mobile on the primary coil, because of the change in current, it will induce a current in the secondary. Secondary coil is inside the mobile, primary coil is inside the pad. This is the wireless charger. Through this primary coil, when an AC current, alternating current flows, it will produce a changing magnetic field. And if this secondary coil is placed on the primary coil, it will induce a current in the secondary. And that current induced in the secondary can be given to the charging port for charging the mobile. Okay, you can see the working. This is the secondary coil. This is the primary coil, and this one is the secondary coil. Now the secondary coil is connected to the charging port of the mobile phone, and it is placed at the back side. And we can put the cover also, because electricity can be induced even through plastic material. Okay, now the phone is placed on the primary, so it started charging.
Thank you, sir.
Thank you.